So here's PRIMAger. So it's a far infrared hyperspectral and polarimetric instrument. On the right, you have a sort of an idea of what it looks like. It is still evolving in shape, but essentially it's a optical and mechanical box with detector focal planes on top of it. And one is the hyperspectral imager, and the other one is the polarimetric imager. So in a nutshell, this is what it is. The hyperspectral imager, which we call the PHI, photometric hyperspectral imager, goes from 24 to 84 micron. I'll explain how it works. It has a spectral resolution of about 10. It works in total intensity with a full width of half max that goes from 4 arcsecond to 7 arcsecond, depending on the wavelength. And the polarimetric imager, the PPI, consists of 4 arrays defining 4 wide spectral bands of R equals 4, and provides you with total intensity as well as polarized intensity maps, or Stokes vector maps, or total intensity, polarization fraction, and polarization angle map. I'll expand on this in a little while. This is the footprint of the imager on the sky. So as I was saying, the telescope delivers us with what I call a field of regard, which is the location in the sky where we can look at. That's about 42 by 24 arc minutes. And within it, we have our two focal planes, the PHI on this side and the PPI on this side. There are still work going on in the optical design that will affect the distance between the center of these two arrays. We're trying to bring it as close as possible. There are implementation design that define the relative location of the arrays within themselves. The important thing is that both focal planes observe simultaneously. So whereas you're interested or not with PHI, it's always on doing a PPI observation and reciprocally. And it's really a mapping instrument. For maps that are smaller than the telescope field of regard, we will very likely, well, we will do them with the beam steering mirror, which in terms of motion is more efficient than the spacecraft. But for degree scale maps, obviously, we will use the spacecraft to map the sky, possibly very likely with the beam steering mirror to provide modulation, time modulation within the observation. So these are examples of what the focal plane looks like, but I will spend a little bit more time in the next slides. So the hyperspectral imager is essentially an SCD mode instrument, and this is done by superimposing on the detectors, so these hexagons are the detector pixels, a linear variable filter. So it means that the spectral transmission varies from bottom to top or top to bottom. Short wavelengths are transmitted at the bottom, long wavelengths are transmitted at the top of this array. So to get the SCD of an object, it means that the object has to scan through the whole detector. If the object only is observed by part of the detector, you only get part of the spectral range. So this imposes a constraint on the observation in the sense that any source for which you want to have the full spectral coverage has to cross the detector in the long direction. So we're using for this a linear variable filter. We are currently running two technical developments, one at Swan and one at Cardiff, and we will select them once we have measured their performance. The polarimetric imager is still using kids, but it's using antenna kids, and the focal plane, so this shape, this diamond shape, is not the one that we'll be using anymore. We'll be using more squarish shapes for the focal plane, and each pixel in the focal plane is of either of these three types. So each is an antenna which is oriented in three different directions. So the important consequence of this is that any measurement that we do with the PPI is in effect a polarized measurement. We're measuring through polarizers. So you can conceive our focal planes as a set of three polarizers superimposed on top of each other, each occupying a third of the surface. And it's by recombining these three measurements that we obtain the polarized intensity as well as the total power. The total power is essentially a sum of these three measurements. And we need to scan this array on the sky in order to recover all the information we need for all the spatial pixels. So that's why PRIMAger is really a mapping instrument. There's no snapshot in the sense there's no staring mode of PRIMAger, because if you stare, you only get single bandpass coverage in PHI. You don't have the full spectral coverage, and it varies along the array. And you are not getting all the three components that you need to measure per sky pixel to derive total power and polarized intensity. So it's designed to map significantly larger area than this intrinsic focal plane of the array, which rises from 1.5 by 3.5 to 5.5 arc minute. So typically, for fields that are, as I said, for fields that are smaller than the telescope field of regard, we'll be using the beam steering mirror. We haven't yet finalized what kind of trajectory would make sense. And for tens of arc minutes to 3 degrees, we'll be using the spacecraft. One important thing to realize, and maybe I'll come back to this slide, is that since the relative positioning of the arrays is fixed, if you want to map the sky with more than one array, you need to account for the fact that they are slightly displaced, much like it was in the fire situation. And so to map a 20 by 20 arc minute common area between all the PPI array, you need essentially to map a 30 by 30 arc minute area so that the common area is about 20 by 20 arc minute. So use margins when you you estimate the size of the map that you need for your object. One important aspect that we've been working on is confusion. We have a 1.8 meter telescope, so obviously the if we don't do anything, the long wavelengths bands of our survey will be limited by confusion and not by the sensitivities of the detectors. So we've already started to do some work in the data processing aspect, and you can check that in this paper, Betterman 2024 and Donnellan 2024. Essentially, what we are relying on is something that Hannah was mentioning, is that there will be a lot of prior catalogs to the survey that we will make, and we will use this prior information to beat confusion. And these papers show that indeed we can go below the classical confusion limit, which is some beams per sources. So I encourage you to read, to look at this paper to see the strategies that we are developing for that. Now the last two tables summarize the some characteristics of the instrument. So again, PHI is the hyperspectral imager, PPI is the polarimetric imager. These are their relative power. Essentially the pixels are arranged in a pattern which is realizing an f lambda center spacing. So there's a correspondence between the full width half max of the expected area function from the telescope and the pixel size. And we're using the mapping and readout strategy to recover the full spatial sampling that we can with the telescope that we have. And these are the sensitivities. These are the required sensitivity, as I was expressing. They correspond to a 5 sigma background subtracted flux limit in a 1 square degree map observed for a total duration of 10 hours with some with overheads as far as we can estimate included. And for the PHI sensitivity, they correspond to to an estimate where we use a sequence of 6 R equals 10 filter that are spanning each band typically. So this is the range from short to long wavelength sensitivity in the band. And the polarized intensity is defined this way. If you want to scale these numbers to your application, you have to use these scalings, but this is implemented in the time estimator. And so this is a summary. So PRIMAger is a high sensitivity mapping instrument that implements hyperspectral imaging using linear variable filter. So hence the need to map the area for which you're interested, and using polarized pixels again on the polarimetric imager, hence the need as well to map. So and if you want more information on recovering polarimetry, it's published there. On surveys and confusion, these are the references. Thank you.
There is a question from Yaolun.
Yeah, so I have a question about the field of view of the PHI. I think it's one of your yeah, but I think in one of the table it mentions about 3 augmented by like 1.5 or something.
Yeah.
And I'm just curious about what that means, like because it's like an instantaneous, basically the block is like drawing here.
Yeah. Okay. This is the so 3 arc minute by 1.5 is the angular size of this on the sky. So what it means is, and the important thing is that if you just project that on the sky, you're not seeing the same part of the spectrum of the source here than the one you're seeing there. And so if you want to, you will start to have a full SED of any object once you have made a motion which is at least 3.5 arc minute in the vertical direction, so that you start to have areas of your sky that have seen the full detector. So typically, you need at least a 3.5 arc minute BSM throw to start having a full sample of initially a very small area, a very small line, and then as long and then getting larger than 3.5, you start increasing the line that is fully sampled.
Okay. Yeah, so it kind of doesn't make sense to do anything like smaller than the augmented.
Yeah, no. Well, if you want to do a map that is 3 arc minutes, you need to say, okay, I need a span of the DSM mirror, which is 3.5 plus 3. That will give you the map.
Right. Okay, thank you.
And I would say a bit similarly to what I was saying to Faris. Now, if you want to map large area, the fact that you have on the sides of your map a 3.5 arc minute that is only partially sampled, because this is the start of the scanning motion, it becomes less and less relevant the larger your map is. So typically, yeah, go ahead.
I just try to confirm, but for the polarization mode, there's no need for doing that, right?
No, for the polarization mode, indeed, the essentially what you could say is that for polarization mode, as soon as you move by an angle that is about the size of these hexagonal cells, you have sampled your pixel with three different pixel types, and so all the information is there. Now, you don't have a lot of redundancy then, so I suggest making larger, slightly larger maps than this anyway. And since it's generally useful to have more than one band, you'll see that because this is typically 11 arc-minute, I'd suggest not trying to do areas that are smaller than like 5 arc-minutes or so in common. So typically maps that are 10 to 15 arc-minutes per array.
So would you say if we for like a survey of point sources, but they're not specifically going to be together? For example, I'm thinking about Stockholm region, they're not necessarily going to be right next to each other.
Yeah.
Would you say maybe Virus is more suitable instrument for that kind of job because the pointing flexibility is a little bit more independent?
It could be, yeah. It could be that if what you're interested is in spectral information on fields that are a few arc-minutes wide, Virus could be probably more effective because you get an instantaneous spectral information. So with Virus you have instantaneous spectral information, and then you need to map to map the spatial area of interest. With PRIMAger, for a small field, you need to map a larger area to not only get the spatial information that you want, but get the spectral information that you need. So so there could be a higher tax there due to that, but really it's something to experiment with the time estimator. Again, with PRIMAger probably gains some speed because of having a lower spectral resolution, but then maybe for your science, R equals 10 is too low. And actually, R equals 10 is the target that we are working for in the hyperspectral linear variable filter development. But I would recommend that you estimate whether the information you're looking for is robust to, say, R equal 8, which could be what we end up with selecting, because the driver science case is SCD of distant galaxies.
Can I ask another question? Yes. Right. So I'm curious about the background subtraction strategy for mapping. Because this is not the OTF map I'm familiar with. So I thought typically you would do like a row and then you observe a background and come back to finish the row or something. But I guess here's
for the one thing that I think the kids detector, they're not absolute, they're not absolute photometer. And furthermore, we expect that there'll be some sort of low frequency drift per pixel. And in the paper that we have made in this paper with Darren, we've implemented some filtering techniques. Typically, right now it's at this stage it was really basic filtering techniques where we apply we look for a baseline per scan of the observation. In this paper, we're simulating small maps, so observations done with the BSM mostly. I think for larger maps, we will have to use more advanced techniques that were developed for Spire and PAX, essentially, where you use the redundancy of the scan to extract simultaneously an image of the source or the field and an image of the drift that affects the field without having to use new high pass or low pass filtering, which affects the structure of the object you're trying to reconstruct. But the result of this is that the zero level of the maps that we will produce will be essentially arbitrary.